In this video, I'm going to teach you how to add or subtract two-dimensional vectors. Two-dimensional vectors are vectors that are added together orthogonally. Now, orthogonal is a word that means relating to a right triangle. And when we're doing two-dimensional vector addition or subtraction, we're doing this orthogonally. This will give us the resultant vector, just as you learned about when we explored one-dimensional vector addition and subtraction. We're going to use both trigonometry and the Pythagorean theorem to do this. So if you haven't watched the last video to get caught up on trigonometry and the Pythagorean theorem, I would advise you to go do that at this time. We're going to start right off with an example problem. Sophia kicks a soccer ball with an initial velocity of 10 meters per second at 15 degrees above the horizontal. Notice the use of relative directions, 15 degrees above the horizontal. What are the x and the y components of the velocity vector? So just as we did with one dimension, we're going to sketch out our vectors. Now in this case here, I've added a horizontal line that is with reference to above the horizontal. I will also have the length of the vectors proportional to the magnitude of the vectors. Our x component, the ball does fly in the x direction or horizontally. The ball does fly in the y direction or vertically. And you can see when I put this together, I have a right angle triangle. Now we're given our angle theta above the horizontal to be 15 degrees. So now we have a plan for solving this problem. We are going to next look at using one of the trigonometric functions to solve for a side of this right angle triangle. So in this case here, I'm using sine theta, which is equal to the opposite side over the hypotenuse. Well, we know the hypotenuse, and you know that we can rearrange this to solve for the opposite side, which corresponds to the y component here. So if I multiply the hypotenuse of 10 meters times sine 15, I can solve that to be equal to 2.6 meters. And we've just now found the y component of the vector velocity. Now, the next thing we can do is use Pythagorean theorem, or we can use another trigonometric function. That's up to you. That's whatever is the most intuitive to you. What I'm doing here is giving you several different perspectives for solving these problems. You're going to hear me in physics say there's more than one way to solve these problems, and I want you to use whichever one's most intuitive to you. All right, let's get back to it here. Using Pythagorean theorem, we can relate three sides of a right angle triangle. So solving for b, we set that equal to the square root of c squared over minus a squared. B, therefore, is the square root of 10 squared minus 2.6 squared. Again, the 2.6 squared, we used a trig function to find that. That was the vertical or y component of the velocity vector. And we can solve for b to be equal to 9.6 meters. And that is the x or horizontal component of the velocity vector. So now we've solved for both the x and y components for this soccer ball. Now you might be saying, can we use some other way? Yes, and I'm proving it to you guys. You can use any trig functions that you want now to relate this to find the x component. They all work, they give the same answer. So again, whatever's most intuitive to you. Now let's do another problem here. A deer walks 10 meters east to a patch of clover. Sound familiar? But this time, the deer turns and runs 15 meters south. Find the resultant vector. We're going to use a Cartesian plane in the coordinate system for this one because our problem is giving reference with cardinal directions. So, going ahead and laying out our vectors on the Cartesian plane, the deer walks 10 meters east. So you know we're employing the same methodology we did in one dimension with our collinear vectors. So we can do the same thing here. We're still using head to tail vector addition. So I want to draw the second vector starting from the head of the first vector, extending in the direction, in this case south, using the cardinal directions on the Cartesian plane. Now you can see we have our hypotenuse, and the hypotenuse is the resultant vector. So we can use the Pythagorean theorem to solve for the resultant vector, which is the hypotenuse. We have A, we have B, so all we're going to do is square these and then take the square root, which is equal to our hypotenuse, or C, which is equal to 18 meters. But we are not done yet. Remember, vectors have both magnitude and direction. So we found the magnitude of the vector, but we still need to figure out the direction of the vector. So let's go ahead and do that now. Looking at this and any of the possibilities that you've learned about in the last couple videos, we can use a cosine function, and we can use the inverse of the cosine function to help us relate the ratio of the adjacent side over the hypotenuse to the angle theta. So using the inverse cosine function, we can solve for theta to be 56 degrees. We're still not done. We need to use cardinal directions to finally finish answering this problem. So let's look at the Cartesian plane, and let's go ahead and get our final answer here. To be 18 meters, that's the magnitude, at 56 degrees south of east. Now that was something you learned about several videos ago. South of east. What else could I say? How else could I describe the direction of this resultant vector? Well, you could also say 18 meters at 34 degrees east of south, and either one of those would be perfectly acceptable. In our last problem here, Sophia is riding her bike. She travels 8 meters southwest, then she turns and proceeds 6 meters due south. She stops to have some of her juice before heading 20 meters at 30 degrees north of east. What is the resultant vector? Let's go ahead, get our Cartesian plane, and start sketching in these vectors from the problem. First and foremost, 8 meters southwest. Well, the cardinal direction southwest implies a 45-degree angle. So she moves at a 45-degree angle southwest, as is shown. She moves then 6 additional meters, but this time she is moving due south. And in the third leg of her journey, she turns and is traveling 20 meters, but at 30 degrees north of east. So 30 degrees north of east would look like this. Now keep in mind, head to tail vector addition. We did this in 1 dimension with 3 vectors. We're doing it in 2 dimensions with 3 vectors, but we're still using the same methodology of aligning the tail of the second vector to the head of the first vector. And then from there, we're aligning the tail of the third vector to the head of the second vector. And when we connect the tail of vector 1 to the head of vector 3, we get our resultant vector. As you can see here, we have our resultant vector. At least we know what it should look like. We have it sketched out. Now we need to actually solve this problem. Taking a closer look so we can really analyze our angles here and solve for the resultant vector, you're going to do the following. Make note, you're going to resolve vectors into their components. In this case, they're x and y components as needed. Clearly, the 6 meter south vector, we don't need to resolve that into components as all of the vector is southward. Then you're going to take your resolved x and y, and you're going to redraw the triangle and solve for the resultant vector. Now let me go ahead and tell you, I'm teaching you the most thorough way of doing this. There are other options for other problems, but in this case here, I'm giving you a very thorough explanation. So what you need to do is to create a table for your x components and your y components so you don't make any careless mistakes. Let's start with the first leg of her journey, 8 meters southwest. Let's look at that. Now, as you can see, orthogonally, again, relating to a right-angled triangle, we have our 8 meter resultant vector shown, and we've resolved it here into both its horizontal and vertical components. So we have our vertical component, which is southward, but there is also a westward component, and together they comprise her southwest vector. So let's go ahead and figure these out. Using trigonometry, you can solve this because you know your angle to be 45. You can also just use your prerequisite knowledge of an isosceles right-angled triangle, relating these two by the square root of 2. So if I take 8 meters and I divide it by the square root of 2, which is about 1.414, you get about 5.65. So a couple different ways to analyze the geometry, and I would invite you to use whatever's most intuitive to you. All right, so now let's add these to our table that we've started here. Our x component is westward. Let's call west negative. So we have a negative 5.6. Our y component is southward. Let's call south negative. So that is also a negative 5.65 meters. Now let's move on to the next leg of Sophia's journey. 6 meters due south. Well, we don't resolve this one, so we can simply add negative 6 to our y component because we are calling south negative. For the third component here, we are going to look at this last leg where she journeys she's at a 30 degree north of east for the direction of the vector. And again, we have our right angled triangle that we're going to be analyzing here. And you can solve this using a trig function of your choice. That's up to you. You've got a refresher on the common trigonometric functions, how and when to use them. So you can solve this. You can say, or you can simply say, I know that sine of 30 is 1/2. So if sine of 30 is 1/2, then this vertical component here is 1/2 of the hypotenuse, because sine of 30 degrees is equal to 1 over 2. That's relating the angle and the ratio. Whatever's most intuitive to you, or grab your calculator and plug it in. It really doesn't matter. But now we have our components. Let's add them to the table here. Positive 10 in the y direction. Let's call north positive. And then we have positive 17.3 meters in the x direction, calling east positive, which means we've resolved all of the vectors that needed to be resolved, and now we can analyze the geometry of the triangle that we will soon redraw to find the resultant vector. Let's look at our x direction. We get a positive 11.65. In the y direction, we get a negative 1.65. So looking at that, we know where we're going to end. In the x direction, we have a positive, overall positive east direction, which you can clearly see on this Cartesian plane. However, for the y components, we have a negative or southward component at 1.65. Again, look at where we're at on the Cartesian plane. Let's go ahead and redraw this triangle here and solve this problem. Again, I'm giving you a very in-depth example here for two-dimensional vector addition, simply because we will spend very little time on the prereq vector component in Physics 1, AP Physics 1. We go straight into it. So you need to have a good understanding of what you're doing, which is why as soon as this video is over, I want you to go and click to the left on petersonscience.com. Go ahead and open up the problem set and work through any of the problems that you would like to make sure you're good to go. Redrawing this triangle here, we can have our positive or eastward 11.65. We have our southward or negative 1.65. And of course, for the resultant vector, we're going to extend a vector from the tail of the first vector to the head of the second vector, and that is the resultant vector. And it forms the hypotenuse of our right-angled triangle. Next, we can use the tangent function here and use the inverse, because we know the opposite side, we know the adjacent side. So an inverse tangent function makes sense. And when we put in these numbers, we get theta is equal to 8 degrees. Now, if you got a negative 8 degrees, that is because the inverse tangent or arctangent function is restricted to quadrants 1 and 4 on the Cartesian plane for reasons that I don't need to get into at all in this video. So having said that, we're going to use our angle, which you see is small. 8 degrees makes perfect sense. Next, we're going to use the Pythagorean theorem to relate these two sides of our right-angled triangle to solve for the magnitude of the vector, which is our hypotenuse, to be 11.8 meters. So now what do we know? We know our angle theta. We know the magnitude of our resultant vector. So now all we need to do is use our cardinal directions, and we can finally give an answer to this question for the resultant vector to be 11.8 meters at 8 degrees south of east. So we are all set here, laying that foundation to be able to work with vector quantities in AP Physics 1. I can't wait to get started. I'll see you guys in class.